All right. Good afternoon, everyone. So it's a pleasure to be back again at this year's AI Hardware and Edge AI Summit. I'm looking forward to tell you a little bit more about who we are as a company at EdgeCortix and really walk you through our journey of building an integrated platform for hardware and software focused on really radically better energy efficient AI processors. We are a little bit over 4 years old company, so still young as a technology company. Our core R&D team is based out in Japan, but we are really at the forefront of technologies where what we call trying to push the boundary of performance per watt, building a lot more power efficient AI processors specifically focused on the edge market. Today, I'm going to try and walk you through our journey in that process. How did we embark on the journey of building such an integrated platform, breaking it down across 3 fundamental challenges that we discovered in that process? I'm sure there are a lot more challenges, but I'm going to focus on 3, given the interest of time, and then try to break that down based on our own experience. How did we start solving those challenges? And then fundamentally, at the end, I'm going to talk a little bit about what are the next steps that we are taking as a company beyond the first generation silicon that we have built, beyond the software and hardware that we are already shipping to a large number of customers worldwide. What is it that we see today in terms of the next steps, both for the semiconductor industry as well as us, in radically innovating across the AI processor landscape and making them a lot more performant as well as power efficient? Okay. So as we have seen over the last multiple months, as well as I would say since yesterday, we've been talking a lot about AI. And it's truly an incredible time to live in. When I started my career before deep learning days, AI, machine learning, we are using them colloquially right now as the same. They are not necessarily the same. But when I say AI, we are really talking about neural networks. And it's an incredible time to live in. We've been living through ChatGPT and large language models, but it's been the last couple of decades which has really changed the landscape of what we can do with AI today. In fact, there are applications that we are coming close to human level performance, and there are niche areas where we are even better than human performance. But that radically growing AI landscape also dictates us to create significantly better AI processors, as we have seen with the radically increasing demand. I think yesterday, during the Microsoft talk, we heard about potentially using nuclear fusion to power the AI processor landscape. So clearly, there's a mismatch between the power requirement as well as the compute complexity requirement of what is driving this radically explosive growth of AI models. So before I break down the challenges of how do we start building AI processors and software to tackle that problem, let me just introduce our ethos. The fundamental focus for us as a company when we started off was, can we create a software-defined acceleration platform that enables us to get near cloud-level performance, but at significantly better efficiency? So I'm talking about power efficiency or compute efficiency, orders of magnitude better speed or lower latencies, which is very important for typically edge workloads compared to the cloud, and then fundamentally better cost. So your operational cost of whatever solution a customer at an enterprise deploys with our solution should be radically cost efficient as compared to a data center solution. Those are the fundamental 3 metrics or KPIs, so to speak, that we are operating under. And here in this slide, I try to break down the landscape of processors that we see today across 2 very simple fundamental dimensions. One, on your x-axis, you have the standard dimension of software 1.0 flexibility. Software 1.0, nothing but standard lines of code that we are all accustomed to, a standard programming paradigm that we are all accustomed to. General purpose processors like CPUs and GPUs are extremely good. They're very flexible. You can run whatever code that you want to run on them in most cases. But then they trade off that flexibility with what you see on the y-axis, that's efficiency. So the amount of compute that you can get vis-a-vis the power requirement of that system is always a trade-off with that flexibility. So when we started as a company, much like many others in the industry, we realized that if we were building silicon for AI, we can live without the general purposeness that you would have in a CPU or a GPU. So rather, we would focus on a domain. That domain, rather than call it AI, I would call it software 2.0, which is not a term that I've coined. I think others in the industry as well. I believe the credit would go to Andre Karpathy, if I remember correctly. But the whole idea is that if you're focusing on the idiosyncrasies that exist in neural networks today and build silicon tailored to that, we can achieve a significantly better trade-off of efficiency versus the flexibility. So we can still preserve a lot of flexibility within the software 2.0 domain, but gain orders of magnitude, and in some cases, 2 orders of magnitude better efficiency, compute efficiency and power efficiency. And that's the core focus of us as a company. So with that quick introduction, let me start breaking down the 3 fundamental challenges that we discovered, and I'll try to walk you through our journey of solving those. It's a tall order to completely solve all of those challenges, but I'll try to share our experience in that process. Challenge number 1, what I would call the elephant in the room, software. I think yesterday in Jim Keller's talk, we talked about hardware versus software. I'll take the opposite end. I think it's very important for us to understand that while we are building hardware, it's very important to create all that hardware capabilities. We are at an AI Hardware Summit conference. But software is really the key driving factor of usability. Any piece of hardware that we bring to a customer, if they cannot really use it as well, if it's not efficient in terms of its usage, it's not really useful. And that's the fundamental challenge. Can we build hardware tailored to the requirements of software 2.0, which is nothing but a graphical flow? And in terms of hardware, a data flow is the best representative of such typical graphs. What you see here is a typical example of a transformers model, not very different from the models that are powering the large language models like ChatGPT or even vision transformers. And what you can see here already, as we again saw in some of the speakers yesterday and perhaps today as well, it's essentially a graphical flow. There's a series of graphical operations that is taking place. Typically in software 2.0 or a neural network, there is no explicitly written code. The code is discovered or learned in the form of the weights. And what you're feeding is the training data. You're giving these neural networks a large amount of training data, and the weights, the outputs are discovered or learned in the process. And that's a fundamentally different approach. And if we can create silicon tailored to use those idiosyncrasies of a graphical structure, it's going to perform better. And we'll see that being realized slightly later. The second related issue with software is a very, very fragmented edge market. Unlike the data center, where you have the luxury of being quite a bit homogeneous, you can have a homogeneous hardware infrastructure, and we have seen that GPUs have worked really well there. The edge market, there is diversity of swap constraints, size, weight, power, vary greatly across a big continuum that we call the edge. There's a big heterogeneity that exists across applications. It also exists across the processor landscape. Typically, when a customer is deploying a solution at the edge, they are not looking to deploy on a singular platform. They are likely combining multiple processors. So you can have an x86 working together with maybe an AI co-processor. You might have an ARM CPU working with an AI co-processor. You might have FPGAs in the mixture in that solution. So how do you create software that can deal with that inherent heterogeneity that exists in the edge market? Challenge number 2. I think this is a no-brainer. And again, we have talked about that many times over the last day or so. There's a fundamental mismatch between what we have seen or have known in the semiconductor industry as the growth driving factor in terms of Moore's law, and whether we believe Moore's law is dead or not, it's a fact that it's not growing at the historical rate it was growing. And clearly, it's also a fact there's a mismatch between the traditional growth of Moore's law vis-a-vis the growth or explosive hyper-exponential growth that we are seeing in terms of AI applications, AI models, whether that's the traditional computer vision NLP speech models that was growing at an order of magnitude more compared to typical Moore's law, or it's the recent transformers, which is growing at 2 orders of magnitude or greater in terms of, I think yesterday, there was some data that talked about 300x, this talks about 750x, whichever number you take, however you project it, it's clearly a huge difference compared to standard Moore's law. This dictates whatever processor and software we are building, we need to radically innovate across the architecture landscape And we need to also embrace system scaling methods, whether that's in the material side, packaging side, various other aspects, that enables us to grow beyond what is possible from typical Moore's law. Challenge number 3. And that's the classic trade-off between performance and power. As I talked about, one of our fundamental ethos was, can we build silicon that has the right mixture of performance, compute, but also does not trade off power for it? If you look at the left-hand side, it's not a very flattering picture of today's AI models. ChatGPT, the large language models, they work very well, but at what cost? There's an enormous amount of power requirement, and it's also unsustainable. I think a couple of years ago, there was a study, I believe from Stanford, and MIT Review published that they talked about the carbon footprint of training AI models is equivalent to the lifetime cost of 4 cars, I believe. It's just enormous. And today, I think recent studies talked about the power footprint or electricity requirement for models like ChatGPT is equivalent to 750,000 people, humans, just enormous. Clearly, there's a mismatch between that power requirement, the model complexity, which we need to deal with, versus how we are innovating in that space across both software and hardware. On the right-hand side, I try to project this across 2 simple dimensions: performance versus power, that we need to trade off typically in any exercise of semiconductor building, whether that's for AI or anything else. And what we really want to be able to do is be in the bottom right-hand quadrant, what I call the zone of high efficiency, where you have high performance, but you're also within acceptable margins of power. And the worst case scenario would be your top left, which I call the zone of uselessness. But you can have systems that give you a lot of performance, but you don't get performance and you have a lot of power requirement. And then you have things in between where you have data centers, which are more, I would say, towards the top right quadrant, and typical edge environments where you have low power, low performance requirements, for example, closer to the sensor, or what we call fundamentally constrained edge devices. We as a company, we have been focusing on the bottom right, the zone of high efficiency. And the second factor is this curve that you see, that's not a static curve. So the key idea was, is it possible for us to dynamically balance this curve? If you can shift this curve horizontally, vertically, and do this dynamically in some manner, we can create the right balance between the requirement of performance and power. So that's the third fundamental challenge. So with those 3 challenges, I'm going to now try to walk you through our journey of solving some of those challenges. The first thing that we focused on, which might be obvious, is the edge. And there's a very clear reason to focus on the edge. As you see here, the edge is where all the data is being generated or created. And data is really what is driving all these AI models. It's not compute, it's not software, but it's really data. Without the data, there's going to be no real usefulness of any kind of AI models that we can create. And where is that data? 75% of all enterprise data is either created or generated at the edge within the next 2 years. And I think that this data is a little bit old already, so probably it's even larger right now. So as a result, if we start concentrating on bringing compute at the seat of the data creation, we eliminate the amount of time it takes to move that data from the edge to the cloud, which is a very expensive process. And memory is very expensive. In fact, in many cases, as we have seen today with the transformer models, memory is the bigger bottleneck than compute. And that's another thing that you can trade off. So you don't need to necessarily have a lot of memory, but you also want to be able to trade off the amount of data movement that you need to do from the edge device versus the cloud. Using that approach, what we started building was a very, very modular and scalable design, almost like a Lego-like building block. We call this a dynamic neural accelerator, which is essentially a runtime reconfigurable data flow architecture created as a single simple building block or a Lego-like structure. Each AI processor block or a DNA core is highly configurable. It can span from limited amount of compute in single core configuration to large amount of compute, fully configurable, fully customizable, depending on the type of solution that you're deploying. And internally, every DNA core essentially has a distributed fabric, along with a runtime reconfigurable interconnect, or a circuit switching interconnect that connects all the different cores together. And you have local memory distributed across each of those compute cores. What this enables, at compile time, you would statically compile your workload. But while you're running your workload, you can now leverage the idiosyncrasies, the different degrees of parallelism that are inherent in a typical neural network to reconfigure how you would distribute that workload across that spatial fabric. Or in other words, you are converting a temporal relationship that you see in a graphical structure to a spatial layout that you would have on that processor. That enables us to now trade off the power as well as compute requirements. For instance, if you're running a model that does not require all the computing power that is available to your processor, you don't need to use all of that. You can switch off certain parts of your processor if you don't need that. That gives you a good balance between compute and power. It also increases your utilization of your chip. In the industry, we have talked about TOPS per watt, but it's really meaningless in terms of actual workload. It is the amount of actual usable TOPS that matters. And that kind of trade-off mechanism would enable you to balance that better. The second piece I haven't forgotten, going back to challenge number one, along with innovations on the processor core, we focused on building a software-centric or a software-first approach where we build a compiler which is tailored for graphical computations, or essentially software 2.0. We call this framework Mera. It works across all the standard machine learning frameworks, whether it's PyTorch, TensorFlow Lite, or ONNX. You can natively bring any of those workloads. And what it does is that it works with an intermediate representation of a graphical structure, as you see here. The next step of the process is to do pattern identification. Given the graphical structure, it now uses, in some cases, heuristics, in some cases, machine learning itself, to identify certain patterns that are repetitive. And these patterns allows the compiler to now decide how to schedule the workload, how to partition that workload across the computing fabric that you have available with you. And it can also be a mixture of heterogeneous processes. For example, in this case, you could partition some of the workload to run on a CPU. That could be x86, it could be ARM, it could be RISC-V. And some of those patterns, if you identify it to be running more efficiently on your neural processing engine, for example, or the AI processor, it gets offloaded to that AI processor. This kind of balancing mechanism, or the heavy lifting of how to partition that workload, is left to the compiler, and the hardware is a lot more simpler in terms of its usage. The software that we created here, because it was designed from a heterogeneous workload perspective, we in fact license it to other third-party semiconductor companies to bring that same value today in production chips with other leading semiconductor companies as well. So it not only works for our chips, but it also enables other companies to leverage their own silicon solution targeted for AI domain to bring the value of a graphical compilation that you see here. And finally, we put it all together, and we brought to market our first generation chip called Sakura. Given our Japan heritage, we decided to choose a name that represented cherry blossoms, or something that brings hope and renewment to the industry. So Sakura is designed essentially as a best-in-class edge AI-focused processor that has the right balance, in our opinion, between performance, power efficiency, future-proofingness, as well as accuracy. And I'll walk you through each of them. In terms of performance, as a single chip, you get up to 40 TOPS or more of compute, while designed for low latency workload. So it was optimized to essentially run streaming data, which is one of the fundamental requirements in most edge cases. Unlike the data center where you can aggregate your data and batch your data in the language of neural networks, you don't have the luxury in most of the cases for edge workloads. You typically have to process the data as it arrives, or in the language of neural networks, we call it batch one. So this was designed to optimize batch one performance. That's where you get the most performance per watt. Power efficiency. At a board level, not at a chip level, at a board level, the power is essentially less than 10 watts in most cases. So you get quite a bit of performance per watt advantage. Third, future-proofness. In terms of our production silicon, we ensured that it not only works for vision models, but it also works with the latest generation transformers, language models, vision transformers. As a result, as we are moving through the landscape, or a changing landscape of AI models, you are not creating silicon that only works for convolutions or vision. It is future-proof in terms of the landscape that we are seeing from a generative AI perspective. And finally, we enable mixed precision support with the right balance of different types of precision such that you can preserve high degree of accuracy. There are many applications where, I think we heard the last speaker talk about quantization. Quantization may not work in certain applications where accuracy becomes very important. Even a 0.1% change could be critical. And that's what we enable through the mixed precision support that is built into the chip. And as a result, today, we make it available in different form factors from a single chip to low-profile cards, standard solutions that are available shipping to customers worldwide in different form factors from full height, full length to low-profile cards, as well as standard M.2 solutions. And then we also make it available with our partners in a mill standard, industrial standard compute box, a fully enclosed solution with the software as well as hardware all integrated together. So what would we get with that? Using that approach, we created a fully integrated software and hardware platform with three key elements. Mera, that's essentially a software platform that not only works for our hardware, but embraces the inherent fragmentation and heterogeneity of the edge market. You can make that work on FPGAs. You can combine different types of hardwares together. You can throw in an x86, an ARM, or a RISC-V. You can leverage and make that work on third-party silicon, as well as use combination of our hardware with third-party software. That has enabled, or third-party hardware rather, and that has enabled us to drastically reduce the AI deployment time from multiple months to mere few days in many cases. And then DNA is the core IP, and Sakura is its generation of different devices that inherently leverage the benefits that we get from the software itself. With that, let's talk about, in the next 2 minutes or so, some performance numbers. Here you can see a comparison of the compute efficiency and area numbers of our Sakura solution compared to, let's call it, the previous generation of leading GPUs on the edge. Of course, there are numbers like MLPerf, and I hope David is here in the audience. I think one of the key issues that we have seen with MLPerf is the fact that we are still relying on Resonate 50. I think everybody would probably agree that Resonate 50 is not really a meaningful number anymore. As a result, here, when we benchmark, we focus on meaningful numbers that we have seen customers use. So here we are using workloads like object detection, YOLO v5, YOLO v8, relevant solutions that customers are coming to us with. So in one of those workloads, I believe this is a YOLO v7 model at a relatively high resolution and mid-resolution comparison. And you can see that we not only have a die benefit, so the smaller size, of course, has a cost impact in the comparable process node, but we are also significantly more performant in terms of compute efficiency and power efficiency. And even when we move to comparing it to a latest generation processor node, for example, a 12 nanometer solution from us compared to a 7 nanometer solution on the GPU side, we're able to still preserve significant performance as well as compute efficiency leadership. In this example, we are using a YOLO v5 example at a relatively high resolution, running at full batch 1. That has enabled us to bring 3 products to the market, from software, IP, to hardware, and we are actively shipping many of our solutions today, including software and hardware, to a number of customers worldwide. With that, in the next 40 seconds, in terms of the next steps, one of the key things that we focused on was not only building the silicon solution, but what comes next. And as a company, as well as an industry, we realized that it's no longer enough to focus on monolithic die solutions like Sakura 1, and we have started focusing on more multi-die integrated system and chip solutions, or chiplets as well. As a result, in the next generation, we are making our solutions available as reusable pieces that allows you to aggregate those solutions and build larger systems when necessary. With that, I'll stop, and perhaps we can take a question. Thank you.
Unfortunately, that's all we've got time for to stay on track. But if anyone does have questions, they can visit the EdgeCortix booth. And you guys will be here today and tomorrow. And we've got a networking break coming up soon. Thank you so much, Sakya.
Thank you, everyone.